Okay, the next chapter that we shall look at is chapter 8, motion in a plane. In particular, we shall be looking at circular motion and applications of Newton's laws. We shall be particularly studying circular motion and other applications of Newton's laws. Suppose we have a particle moving in a plane, a flat plane, in a circular path. So let's consider a particle of mass m moving with a uniform speed v in a flat circular path of radius r. The particle experiences an acceleration given by a subscript c, where a subscript c is called the centripetal acceleration. A subscript c is given as v squared over r, where we are saying that v is the speed of the particle in the path, and a subscript c is the centripetal acceleration pointing to the center of the path, and the radius of the path is r. Okay, so the centripetal acceleration is v squared over r. So we can apply Newton's second law to this motion to find the force causing this object to accelerate. So we shall find the force causing this centripetal acceleration by using Newton's second law. So Newton's second law tells us that the net force is equal to m times a, and so the centripetal force, which is the only force present, is going to be equal to the mass times the centripetal acceleration, which we can write as mv squared over r. So the centripetal force is mv squared over r, so it only remains now to find the force and what causes that centripetal force. So we can analyze various scenarios to determine the centripetal force. So let's start off by looking at the motion of a vehicle on a flat circular path. So scenario number 1, motion of a car on a flat circular track. So let's draw the scenario. So we have a circular track that looks like that, and we can draw a car with wheels, and this is it. So we say that the force pointing to the center is the centripetal force. The vehicle, of course, has weight mg pointing down and support force F subscript n. We consider that the support force F subscript n is the total force from the four wheels, and F subscript c is also the total force. So let's apply second law again. So we say that the object is moving with a velocity v, which is at a tangent to the circular path, or the vehicle moves with velocity v at a tangent to the circular path. So the forces present are the support force Fn, which is equal to the weight mg, and then we have the frictional forces. There is a frictional force at each wheel, which is a static frictional force, which is equal to mu k, mu s times Fn. Okay, let me make a correction. So instead of F subscript c is, we use F subscript c for centripetal force. So I want to call this the static frictional force. These are the static frictional forces. So Fs is maximum static friction at wheels. So I've changed the label. Instead of Fc, I'm calling it Fs so that we don't get that confused with centripetal force. So these are the forces acting on the vehicle. So we can write Fs, which is the maximum static friction, to be equal to mu subscript s mg. Note that mu subscript s is the coefficient of static friction. This is the coefficient of static friction. So apply second law now. And what we have is the net force is equal to the mass times the centripetal acceleration, since the vehicle is moving in a circular path. And the external force present is the static frictional force, and that should be equal to mv squared over r, where r is the radius of the circular track. Okay, and we already said v is the speed of the vehicle as it moves along this circular track. M is vehicle mass, and that should be in kilograms. R is the radius should be in meters. So centripetal force is due to the static frictional force mu s mg, and that should be equal to mv squared over r. From that we can calculate that v squared is equal to mu s g times r, where the masses cancel out. So we can say v is the square root of mu s g r. This tells us that for a vehicle on a flat circular track, the speed v depends on the coefficient of friction between the wheels, and I'm referring to static friction, the acceleration of gravity g, and the radius of the path. Note that for the case of a vehicle moving on a flat circular track, centripetal force is due to the static frictional force between the wheels. So F centripetal is due to the static frictional force between the wheels. Let's look next at the motion of a vehicle on a banked circular track. So this time I will draw a banked circular track like that, and let's say we have a vehicle moving on this banked circular track that way. It has the wheels that way. So if we look at it from the end, if we look at it endwise, then what we have is, so this is the, let's say this is velocity v. So if you look at it endwise, then you're going to have the wheels that way. And so what we have then is the, let's have the weight acting vertically downwards, F subscript g. The angle theta is the angle of the banked track. And then we're going to have the support force, F subscript n, not uppercase n, let's change that to lowercase n. This is the support force, F subscript n. And then we shall have the radial component of the support force and the vertical component of the support force that way. So this angle is theta. So our angle here is also theta, like that. So we've identified the various forces on a vehicle on a banked circular track, which is banked at an angle of theta. So let's consider the vehicle of mass m on a track banked at angle theta, and let's say the vehicle moves at velocity v around this circular track of radius r. So we've identified various forces on this vehicle. So let's look at the vertical forces first. The vertical forces acting on the vehicle will be the F subscript v and the weight of gravitational force F subscript g. So Fv is equal to Fg by Newton's second law, okay? And F subscript v, which is the vertical component of the force or the support force, is equal to the weight mg. F subscript v can be written as Fn cosine theta, where F subscript n is support force, and I've already labeled F subscript g to be the weight. And then the next thing is horizontal component of the force. Well, let me make a point here. Note that in the vertical direction, there is no acceleration. That's why I set Fv equals Fg. So I just applied the second law, and I said that the vertical component of the support force minus the weight Fg should be equal to ma. Therefore, since a is equal to 0, that is, I get Fv equals FG above. So that was what I did to get that result. So I just wanted to make that clear to you. Now let's consider next the horizontal component. And in the horizontal case, the horizontal forces are the horizontal component of the support force F subscript R, and that should be equal to M times centripetal acceleration A subscript C, where AC is equal to V squared over R. R is the radius of the circular path and V is the speed of the vehicle in the path. Fr is equal to Fn sine theta. Therefore, we can say Fn, which is the support force sine theta, should be equal to mv squared over r. And then we can say that from the vertical portion, we know that Fn cosine theta is equal to mg. This is what we found over here. Fn cosine theta is equal to Fg. So from this, we can see that the centripetal force is due to the horizontal component of the support force. So we can say that in the case of a vehicle on a banked circular track, so let's say in the case of a vehicle traveling on a banked circular track, the centripetal force is due to the horizontal component of the support force, F subscript N. And let me make a point to show you that Fr is equal to Fn sine theta and Fv is equal to Fn cosine theta, just to be clear. And then let's put this down that way. Okay, so now we can go on. Let's continue our analysis from the two functions. Fn sine theta equals mv squared over r, and Fn cosine theta equals mg. Let's eliminate Fn by dividing the two formulae. So we can say that Fn sine theta divided by Fn cosine theta is equal to mv squared over r times 1 over mg. So I'm dividing the two like that. I can cancel out your m's, cancel out those, and we have tangent theta. So notice that sine theta over cosine theta is tangent theta, of course. So we'll say that tangent theta is equal to v squared over rg. Therefore, v is the square root of rg tan theta. This tells us that the speed of a vehicle traveling on a flat circular the speed of a vehicle traveling on a banked circular track depends on the angle of the track, the radius of the track, and acceleration due to gravity. Okay, so we've got that down. Let's look next at a pilot in a vertical loop. So let's analyze next the motion of a pilot in a vertical loop. So draw the vertical loop that way, and let's say that at the bottom of the loop, the pilot will be sitting in an aircraft that way. So this is the aircraft, and the pilot will be sitting this way, moving with velocity v to the right. So let's say v subscript b for the velocity at the bottom. The radius of the loop, of course, is r. And at the top of the loop, we have our vehicle, our aircraft this way, and the person will be sitting this way in the aircraft. And the velocity is v subscript t, velocity at the top. Let's consider the top and the bottom motion separately. So first we can look at the top motion, and then we shall look at the bottom motion. And let's make a division here. So for the top motion, I'll just draw that by itself. Pilot is sitting this way, so we're going to have here, let's have here the weight mg, of course, and then we shall have a support force Fn. pointing down that way. And then for the bottom portion of the motion, again, we have pilot sitting in the aircraft that way. So we're going to have the weight mg acting vertically downwards, and the support force is this time Fn pointing up. And then we apply Newton's second law to each scenario. So here we have V top, of course, Vt, and this is V bottom. We know the net force is equal to mv squared over r, where the net forces would then be just the forces present, which would be the support force Fn. It's pointing downwards, so we put a negative sign, minus the weight mg, and that will be equal to minus ma centripetal. So everything is pointing downwards when the pilot is at the top. So we can say that Fn plus mg is equal to mv squared over r. So this is the speed at the top divided by r. And do the same thing for the bottom motion. Apply second law, and we see that the net force is equal to ma centripetal. The forces present are the support force, and the weight is pointing downwards, so that's opposite, so minus mg. And since the centripetal acceleration is pointing up, we have positive ma centripetal. So we can say that the support force Fn minus mg is equal to mv bottom squared over r. So we found our two forces present on this pilot. So let's continue here. So again, this is top and this is bottom. We have a division between them. So F subscript n can be written as mv at the top squared divided by r minus mg, and F subscript n in this case can be written as mv subscript b squared for the bottom divided by r plus mg. What all this means then is the support force is the apparent weight of the pilot. So F subscript n is apparent weight. In this case, pilot feels lighter at the top of the motion or at the top of the loop. Pilot feels heavier at the bottom of the loop, since Fn is again apparent weight. So what we've seen with these analysis of various scenarios is that we can identify the centripetal forces on an object. We can identify the forces that produce the centripetal force, and we can also, in the case of the pilot in the vertical loop, we can identify the apparent weight of the pilot as the support force F subscript n. In the case of the pilot, the centripetal force is a combination of the two forces, the support force and the weight. So those are the centripetal forces, and they are separate for the top force and the bottom force. Centripetal forces are different at the top and at the bottom. This explains why in a pilot traveling in a vertical loop, they have to maintain their speed. They have to be going fast at the bottom and also going at a minimum speed at the top in order not for the plane to stall. We can actually analyze that scenario to find the minimum speed required to avoid stalling. So let's look at the example. So to avoid stalling, we need the plane to continue moving at a certain minimum speed throughout its entire motion. So at the top of the motion in particular, let me rewrite this. So the plane does not stall at the top of the loop. So at the top of the loop, this is what we had. So the person or the pilot sits in the plane that way. And we found that at the top of the loop, Fn plus mg equals mv top. For the plane to stall, Fn goes to 0. So we want minimum speed where Fn is 0. And so for that scenario, we can say that mg is equal to mv top squared or mv top min over r. So we can say v top minimum squared should be equal to g times r. If you just cancel out the masses. So the minimum speed required should be equal to g times r. So v top min is equal to the square root of gr. So for a plane not to stall, the speed should be the square root of the acceleration of gravity multiplied by the radius of the loop. Let's look next at non-uniform circular motion. So for non-uniform circular motion, we are saying that the speed is not fixed, the speed v is not fixed, and so there's an acceleration in the circular path. So let's draw our circular path again, and this time we have our speed v like that, and we have our centripetal acceleration, which is the radial acceleration that way. And since the speed is changing, let's say that there is an acceleration which is a subscript t, or tangential acceleration. With that tangential acceleration, we can have a parallelogram which allows us to draw the actual acceleration a that way. So we have a subscript t, which is equal to tangential acceleration, and then a subscript r is our radial acceleration, which is what we were calling centripetal acceleration earlier. V is the speed. This is speed in the circular path. This is changing, so this speed is changing. Note that since the speed is changing, we can say tangential acceleration is equal to dv dt, where v is your speed in the path. So tangential acceleration is dv dt, where v is equal to r omega, so that a tangential is equal to dt r omega, which can be written as r d omega dt, which is equal to r alpha. Therefore, a tangential is equal to r alpha. And then our radial acceleration is just equal to, note that ar is radial acceleration is equal to v squared over r, which is the same as omega squared r. Therefore, a radial is equal to omega squared r. So with this information, we can now write our kinematic equations that we found a few lectures back. So these are the kinematic equations for circular motion. So we have, for the final angular displacement, we have our initial angular displacement, angular velocity initial delta t plus 1/2 alpha delta t squared. We also have omega final equals omega initial plus alpha delta t, and then omega final squared is equal to omega initial squared plus 2 alpha delta theta. Our acceleration in the circular path is a squared equals a tangential squared plus a radial squared. So we can say a equals the square root of tangential acceleration squared plus radial acceleration squared, so that the net force in non-uniform circular motion is F net equals ma, where a is above.